All right, so this is the last lecture in the non-parametric statistics section of the course. So this lecture set is the one that covers what is called the Kruskal-Wallis test. So as a recap, we have studied 4 non-parametric tests, one of which we don't really use, which is the sign test. So we have sign / signed rank test. These are alternatives to the one sample t-test / paired 2 sample t-test. Then we have the Wilcoxon rank sum test. This is an alternative to the 2 sample, or rather the independent 2 sample t-test. Okay, and then we have what we're studying today, which is the Kruskal-Wallis test. And this is the alternative to the one-way ANOVA. And then it's March 12th. Okay, so we're not going to waste a lot of time going through details here. We're just going to get right into the test. So again, the purpose here is the same as what it was in the previous lecture sets. Basically, we have a set of data. In this case, the data set contains 3 or more different groups or treatment levels. And we want to make a comparison between the center of each of those different treatments. But the issue is that we cannot assume normality. So a good example of this would be from the lab assignments. When we were studying the effect of the diets on those mice in the lab assignments, we noted that the normality assumption was not intact for the mice. So the Kruskal-Wallis test is a natural alternative procedure that we can utilize to test for a difference across the different levels of the diet without requiring the normality assumption. Okay, so again, just like with the Wilcoxon rank sum test, which would probably be the most or the most logical comparison, we are using this to determine if there's evidence of a difference between 2 or more independent groups, but we do not require the normality assumption. And just like with the Wilcoxon rank sum test and with the signed rank test, we're going to be utilizing ranks of the observations to determine where the differences lie. So a Kruskal-Wallis test can be carried out in 6 steps, just like any other hypothesis test. The assumptions of the test are that we have an SRS for each population, the samples are independent, and the treatment populations have the same shape. The null hypothesis states that all population medians are equivalent versus the alternative that at least one pair of treatment medians differ. So again, the same idea as a one-way ANOVA, except that we're phrasing the test about the medians rather than the means. On step 2, we state the significance level, and on step 3, we compute our test statistic, which we call the H value. Now notice that unlike a one-way ANOVA, we don't have an ANOVA table. We have a literal test statistic that we can compute using the values in the data set. So you'll see here that we have N subscript J, and R bar subscript J. So that's total sample size for each group, and the average value of the median, or the average value of the ranks for each group. And we're going to go through calculations to see how this works momentarily. On step 4, we can take either the critical value approach or the p-value approach. We will show that the test statistic capital H is a chi-square random variable, which means that we have to utilize the chi-square table of values to determine if we have evidence for or against the null. The chi-square table you would have seen in Stat 151, so I'm not going to go through a lot of detail on what the chi-square random variable is and that sort of thing. We're just going to jump into using the table. For the most part, it works exactly like a t-table anyway, so there's not a lot of explanation that's required. Okay, given our result on step 4, we can then reject or not reject the null, and then we state our conclusion. Okay, so again, this is a alternative to the one-way ANOVA, mainly when the normality assumption is not intact. All right, so the test utilizes the average rank of each sample. So the average rank would be found in the same way as any other average. You add up all the ranks for each sample and divide by the number of observations in that sample. If the null hypothesis is true, we would expect the average ranks to be approximately equal across each of the samples. So we would expect the average ranks to be very similar between sample 1 and sample 2, sample 1 and sample 3, sample 2 and sample 3, etc. If we have evidence of a difference, then we would expect a large variation among the ranks. So we would expect the means to be quite different from each other. And as a result, we would expect, the averages of the ranks, to be quite different from each other, because that's what would increase variation. If we have average ranks that are very similar in value, the variation is going to be really small. If we have average ranks that are very different, the variation is going to be really large, and that would indicate evidence of a difference. All right. So the test statistic for the Kruskal-Wallis test is actually derived from a comparison of different sum of square values about the average ranks. So let's consider two different sums of squares, the sum of squares treatment and the sum of square total. So you can see the sum of square treatment has the same setup as any of the sum of square treatment values that we've seen in the course. It's simply the square difference between the average rank and the overall average rank. So sorry, between the square difference between the average rank of each sample and the overall average rank. The sum of square total is simply the square difference between each rank and the overall average. So these are very familiar formula to what we had seen in the parametric case, except that we're not working with the raw data, we are working with the ranks of the data directly. All right, so the test statistic is effectively a ratio of the SSTR to the SS total over n minus 1. And that gives us the formula that was introduced in the 6-step summary of the Kruskal-Wallis test. So just like in a one-way ANOVA, where we compared SSTR to SSE we compared MSTR to MSE to find our test statistic. And the rationale was if there's a large variation between the groups compared to within the groups, that would give evidence of a difference. Here we have a similar analogy, except that we are standardizing by the MS total rather than the MSE. So now we're basically just saying, if there's a large variation between the averages compared to the overall variation among the ranks, then we would have evidence of a difference. So it's a very similar rationale, but it leads us to a closed form test statistic, which we can utilize to check for a difference among the treatment medians. All right, it turns out that our test statistic is a chi-square random variable. So the chi-square distribution is again a right skewed distribution that is centered at 0, but it only has a right skewed distribution whose lowest value is 0, but it only has 1 degree of freedom, which in this case is the number of treatments minus 1. We're going to use this value the same way that we have every other value we've considered in this course. So if the test statistic is inside a rejection region where the critical value is a chi-square value, we can reject the null. We're only going to do this in one tail because again, the chi-square curve is a right skewed curve. Or if the test statistic gives us a p-value that's less than alpha, we can reject the null. And that's the same rationale we've used throughout the course. All right. So let's dive into an example so we can see how this works. Just before I start, does anyone have any questions about sort of the rationale for what we're doing here? Or can I assume that everyone's kind of on board with what we're trying to accomplish? Sorry, one second. I thought that was a little louder than usual. Okay, so let's work through an example of the Kruskal-Wallis test. So we have the measurements below are the amounts of low-fat milk consumed in 1980, 1990, and 2000, according to the US Department of Agriculture. At the 1% level of significance, do the data provide sufficient evidence to conclude that there is a difference in the median consumption of low-fat milk between the 3 years? All right, so we'll start off with the assumptions here. Now, one of the major assumptions is we cannot assume that the data is normally distributed. So if we were to do a residual analysis here, we would expect to see deviation from normality. All right, so as a starting point, we would say assume there is evidence to suggest that the data is not normally distributed. Okay, so therefore, use a Kruskal-Wallis test. Okay, so again, the main assumption that we're working around here is that normality assumption. So this is an alternative to the one-way ANOVA, which depends on normality and constant variance. But we're saying here that there's no evidence, there is some evidence to suggest it's not normal. So the Kruskal-Wallis is a natural alternative. Okay, so our assumptions here are SRS with NJ greater than 5. Okay. 2, we would have independent samples and 3, we would have same shape in each group. Okay, so if we can assume, well, we don't really know for sure, but let's assume that these are simple random samples, but it doesn't state clearly. We can definitely tell that the sample sizes are greater than 5, right? So for 1980, we have 1, 2, 3, 4, 5, 6, 7, 8. So N1 equals 8. For 1990, we have 7. And then for 2000, we have 9. All right, so we'll assume that this one is okay. I think it would be fair to assume that the samples are independent because they come from separate years. So it's unlikely they're sampling the same persons or states wherever the measurements come from. And then for the same shape one, we would actually have to check this. So we could do things like compare box plots / histograms for each group, or for each year. Right. So we're not totally sure if the shapes are the same, but I would assume, given the variable that we're measuring in the different years, that these shapes should be pretty similar. But again, we would have to check this to be sure using some kind of visual assessment. So histogram and the box plot would be the natural visual assessments that we could utilize. Okay, so on step 1, we have H0, eta 1 equals eta 2 equals eta 3 versus HA at least one pair of medians differ. You could also say not all medians are the same. That would be the same alternative. Then on step 2, we have our significance level, which is the 0.01 level in this case. We're being fancy. All right, now on step 3, we have capital H is equal to 12 divided by n times n plus 1 multiplied by the sum from j equals 1 to k, which is 3 in this case, of little nj multiplied by r bar j minus n plus 1 over 2 squared. Okay, so what we need to do now is figure out what is r bar j. Okay, so the way that this works, going back to the first table, what we have to do is rank all of the observations in the data set. So let's build a table of ranks. So I'll call this table of ranks. Okay, we're gonna have 1980, 1990, and 2000. Now, the way that we do this is we rank all of the data as a whole. So in that sense, it's actually very similar to the Wilcoxon rank sum test. So we move across the data set and we assign values based off of where they're placed in the data, essentially. So to do this, we would actually have to order the values first off, but I have the ranks worked out, so I'll just show you where they fall for this particular illustration. Okay, so, and actually just to make it a little more clear, I'll put a counter down the side here. All right. It's going to be slightly out of room. All right. Okay, so observation 8 from 1980 gets rank 1. So 8.3 is the smallest value in the data set. Observation 3 from 1980 gets rank 2 because 8.6 is the next smallest value in the data set. Observation number 5 from 1980 gets the third rank because 9.2 is the next smallest value. So we're ranking from smallest to largest across the data as a whole. Observation 4 gets the fourth highest rank because it's the fourth highest value in the data set. 10.7 gets the fifth highest rank. 11.1 gets the sixth highest rank. And now we're finally going to switch samples here, and observation 1, 2, 3, 4, 5 from 1990 gets the seventh highest rank. So again, we're ranking across the data as a whole. Okay, now for rank 8 and rank 9, we're going to have a tie between 11.6, which is observation 1 in 2000, and 11.6, which is observation 7 in 1980. So to break the tie, we take ranks 8 plus 9 and we average them. Okay, so this is going to be 8.5, and then here we're also going to have 8.5. Okay, so the same tie-breaking method that we utilize for the rank sum test and for the signed rank test. Take the number of ties, assign the ranks that should be assigned, and then average them. Okay, so now we've assigned ranks 8 and 9, so we're on to observation 10, or rank number 10. That goes to 11.8, which is the sixth observation in 2000. Okay, and then rank 11 is the second observation from the year 2000. Rank 12 is the fifth observation from the year 2000. Rank 13 is the seventh observation from the year 2000. Rank 14 is the fourth observation from the year 1990. Rank 15 is the eighth observation from the year 2000. Rank 16 is going to be the sixth observation from the year 1980. Rank 17 is the first observation from 1990. Rank 18 is the ninth observation from 2000. Rank 19 is the second observation from 1990. Rank 20 is the third observation from 1990. Rank 21 is the seventh observation from 1990. Rank 22 is the sixth observation from 1990. Rank 23 is the fourth from 2000, and rank 24 is the third from 2000. So another thing to keep in mind here is that little n is n1 plus n2 plus n3, which is 8 plus 7 plus 9, which is 24. Okay, so we're assigning from rank 1 to 24 across the entire data set. All right, so now we have the ranks for each of the values under consideration. So the average rank is going to be the averages of the values for each of the different years. Okay, so for example, for 1980, R bar 1 is equal to 6 plus 5 plus 2 plus 4 plus 3 plus 16 plus 8.5 plus 1 plus 1. Yeah. Sorry, just ran out of room. Plus 8.5 plus 1 divided by 8. Okay, so that gives us 5.688. For 1990, it's the same idea. So R bar 2 is going to be the sum of the ranks. So the sum from I equals 1 to little n2 of Ri over n2. So that's going to be 17.143. And then for 2000s, we have R bar 3 is the sum of the ranks. So 1 over n3. I'm definitely not going to have room to fit that. But same idea. So we add the ranks together for the year 2000. So 8.5 to 18, divide by the number of ranks, which is 9. And that gives us 14.944. Okay, any questions? Okay, so now we have 12 over 24 times 24 plus 1 multiplied by 8 times 5.688 minus 24 plus 1 over 2 squared plus 7 times 17.143 minus 24 plus 1 over 2 squared plus 9 times 14.944 minus 24 plus 1 over 2 squared. All right, and then that should give us 11.518. Any questions? Yeah, it's like it's a constant. It's kind of weird, right? Like why 12? All right. Okay, so now all we have left to do is determine if this warrants evidence for rejection or does not warrant evidence for rejection. So that's going to work in the usual way. Now, again, we are using a chi-square curve now, so we can take the critical value approach, or we can take the p-value approach. In either case, we sketch out a chi-square curve, which is basically the same sketch as what we had for the one-way ANOVA. It's a right-skewed curve, right? So we have the following. Okay. All right, so our critical value is going to be a chi-square on 0.1 and 2, because the critical value is on the significance level and the number of groups minus 1. So we have 3 groups, so 3 minus 1 is equal to 2. Okay, so now we go to our chi-square table. We're going to match 0.01 to 2, and that gives us 9.210. So the critical value for this test is 9.210. All right, and then our test statistic was 11.518. So we have H here. So based off the critical value approach, we can reject the null. Okay, if we take the p-value approach, we have capital H equals 11.518. Our p-value is the area to the right of the test statistic. So we have p-value is equal to the probability that the probability that a chi-square exceeds 11.518. Right. So now we go back to our chi-square table. We have 2 degrees of freedom here. Our test statistic is 11.518, so that falls here. Okay, so that means that the area to the right of 11.518 must be smaller than 0.005. So you can see that the way the chi-square table works is exactly the same as the way the t-table works. So we can say since the probability that a chi-square exceeds 11.518 is less than 0.005, then the p-value is less than 0.005. Okay, so then based off of either approach, we can reject the null. And then we can say at the 1% significance level, the data provide sufficient evidence to suggest that there is a difference in the median amount of milk, low-fat milk, I think, consumed between 1980, 1990, and 2000. And there you have it, the Kruskal-Wallis test for median difference. Any questions? Okay, so we're gonna look at another example of a Kruskal-Wallis test now. But what we're gonna do is we're gonna follow this up with a discussion on how you would construct multiple comparisons falling out of a Kruskal-Wallis test. Since we are using a non-parametric procedure to check for a difference among a collection of means, if we wanted to do a multiple comparison, we would follow that up with another set of non-parametric tests. So if I use a Kruskal-Wallis test and I determine that there's evidence of a difference between the medians, what test would I then use to check the pairwise combinations? Any ideas?
Is it the Wilson-Cox test?
Which one?
Or the...
It does start with Wilcoxon, but there's two technically.
Oh, the rank sum test?
Yeah, the rank sum test. Very good. So if we're going to do a Kruskal-Wallis test and we want to check for and then we want to perform multiple comparison, we're going to follow up with a Wilcoxon rank sum test. Now there's two things that we have to consider when we do this. We still need to account for experiment-wise error. So we need to adjust the experiment-wise error for the number of multiple comparisons. And then we would be comparing, for example, our p-value from the rank sum test to the adjusted significance level. The second thing is that every time we perform a Wilcoxon rank sum test, we have to re-rank the data. So in that sense, it is a bit of a pain. So to illustrate that, we're going to consider the following example. So we have plants were grown under three conditions: control, treatment 1, and treatment 2. The table below gives the weight of each plant at the end of the experiment. Okay, so we have the weight in grams of each of 10 plants that were subjected to 3 different treatments. So we have 3 different sample sizes. N1 is 10, N2 is 10, and N3 is 10. The values and the ranks are given in the table on slide 11. Okay, so underneath control, treat 1, and treat 2, we have the weights of the plants. Underneath rank, we have the rank, when again, we're comparing across the entire data set as a whole. So we're assigning from rank 1 to rank 30 across the full data set. Okay, at the 5% significance level, is there evidence of a difference between the central tendencies of each median? Okay, so the first question we're being asked here is the standard Kruskal-Wallis style question. So we want to do a general comparison of all 3 treatment means at once. So that would be a Kruskal-Wallis test. Part B says, should researchers conduct a multiple comparison between the treatment medians? And then how would they go about doing that? Okay, so if we wanted to conduct a multiple comparison, or what I should say is, we would conduct a multiple comparison here for the same reason we did in a one-way ANOVA experiment. If we have evidence that the median values are different, then we would go and perform a multiple comparison about those values. How would we go about doing that? As was just pointed out, we would use a rank sum test. Okay, and then we're actually going to conduct the multiple comparison if we need to. All right, so on slide 12, we have the Wilcoxon rank sum, or the Kruskal-Wallis test being written out for us. So just like before, we have H0, the medians are equivalent, versus HA, at least one pair are different. We're testing at the 5% significance level. On step 3, we're computing our test statistic. So you can see the computation of the test statistic here follows directly from what we did in the previous exercise. Notice again that we have that value 12. That's constant across all Kruskal-Wallis test statistic calculations. Again, the R bar J here are the average rank. So this is the sum of the ranks from each sample divided by the sample size. So on the previous slide, we had 147, 103.5, and 214. The sample sizes are 10 for each of them. So you can see that now we have 14.75. Yeah. Which is 147.5 over 10, right? Then we have 10.35, which is 103.5 over 10. And then we have 21.4, which is 214 over 10. Right. In this case, our test statistic is 504.5725. So that's very large. So the critical value for this test is a chi-square on 2 and 0.05. So you can see that that's 5.991 and is easily verified from the chi-square table. And then the p-value is less than 0.005, which is for the same rationale as before. 504 is much larger than the largest listed critical value, right? So we have 10.597 here, but our test statistic is 504. So that's obviously the biggest, or much bigger than the largest value. So that would mean the p-value must be less than 0.005, which is shown here. Okay, so given that that is the case, we can clearly reject the null. And then we can say at the 5% significance level, the data provides sufficient evidence to conclude that there is a difference in median weights of plants grown under the 3 experimental conditions. All right, so with that being said, would we want to conduct a multiple comparison? Well, yes, we would, because we rejected the null. So we found evidence of at least 2 medians being different. So we would like to determine where that difference lies. So again, you can see the same rationale that we had for the one-way ANOVA. Okay, it's a non-parametric test, the Kruskal-Wallis test is. So we're going to follow that up by doing multiple comparisons using the Wilcoxon rank sum test. All right, so we're going to have, for this illustration, m is equal to 3 choose 2, which is equal to 3 comparisons. All right, so we're going to compare control to treatment 1, control to treatment 2, and treatment 1 to treatment 2. Okay, so those are the 3 comparisons that we're interested in. On slide 13, we have control versus treatment 1. So you can see that what we have to do here is we have to re-rank the data. Okay, so we take control and treatment 1 on its own. So we've isolated those 2 groups of data. And now we have ranked from 1 to 20. Okay. All right. Our null and alternative hypothesis will be that there's a difference because multiple comparisons are two-tailed tests by design. Our significance level is going to be the adjusted experiment-wise error rate. So this is going to be alpha E divided by 2 times M. Okay, so that gives us an experiment or a comparison-wise error rate of 0.0083. On step 3, I'm using the normal approximation to the z-score. Okay, so I have W naught is 122, which is the sum of the ranks for sample 1. I have mu1 is 105, and sigma 1 is equal to 13.22876. These values are calculated using the formula given in lecture set 10 under the normal approximation to the rank sum test. This gives us a z-score of 1.322875, which means that we have a p-value of 0.1868 and a critical value of 2.395. Right? So in this case, we do not reject. So there's no evidence of a difference between the median of the control and the median of treatment 1. Okay. Does anyone have any questions? Do you have a question? Okay, so everyone's okay with this. You understand where the values are coming from and whatnot. So this is just basically just a summary of how a Wilcoxon rank sum test would play out. So everything that's on slide 13 here is taken from lecture set 10. So this is just another illustration of the rank sum test. All right. So now we would have to do the same thing for the other 2 comparisons. So in comparison 2, we have control versus treatment 2. So you can see the null and the alternative here are A to 1 not equal to A to 3 in this case. We have the same alpha star. Now our test statistic is a value of 80. We have mu1 is 105, sigma 1 is 13.22876, and then we have the z-score of negative 1.889. And that corresponds to a p-value of 0.0588. And you can see the critical value is 2.395 in this case. So again, we would not reject. So now we can say there's no evidence of a difference between the median of the control group and treatment 1. And there's no evidence of a difference between the median of the control group and treatment 2. So our last comparison is treatment 1 to treatment 2. Again, we have to re-rank the data. So every time we do the multiple comparison, we have to re-rank. So now we have A to 2 versus A to 3 in a two-tailed test, the same alpha star. And this time we get based off of our test statistic of 71, we get a z-score of negative 2.57. This returns a p-value of 0.01 in this case. Which is compared to a credit. There's something wrong here. Sorry, one sec. Doesn't make sense. Oh, that's weird. Huh. What a bizarre situation. It's very rare, but yeah, the p-value and the critical value approach don't agree here, which almost never happens. Okay, notice between CV and p-value. Very rare. Wow. Okay, so in the situation, I mean, we can see from the critical value approach that we're definitely within that lower rejection region, so that would imply rejection. But the p-value is technically larger than alpha star, so that would imply that we do not reject. Very interesting. Yeah. So in this case, I've written that we should reject. We would expect that we should reject somewhere based off of the result of the Kruskal-Wallis test. I'm not sure if you guys are going to run into this type of conflict in your on the assignments and whatnot, or on the lab assignment, so it shouldn't be an issue. But it is interesting to see that because it's almost never happens. But if we take the critical value approach, yeah, so if we, based on the critical value approach, we can reject here and then say that there's evidence of a difference. It just feels like that's wrong. Like there's something that I'm not accounting for, but maybe, that's weird. All right. Okay, so that's just an illustration of how you do the Kruskal-Wallis followed up with a multiple comparison via the Wilcoxon rank sum tests. And that brings us to the end of the unit on non-parametric tests. So now we have seen 4 different non-parametric tests. We're really only going to focus on 3 of them, though, which are the signed rank test, the rank sum test, and the Kruskal-Wallis test. So for example, in the labs, we're only going to see examples of those 3 types of procedures. As I highlighted at the start of the lecture, each of the different tests is an alternative to one of the non-parametric tests we studied earlier in the course. So we're mainly using these when the normality assumption cannot be verified. For the most part, these tests have a very, or a much less strict, they have a less strict set of assumptions, but there are assumptions like the shape has to be the same for each population. So we do have to check these things. And in lab, we'll look at ways of doing this via, for example, box plot and histogram construction, as those would be natural choices for checking the assumptions of shapes being the same. Otherwise, again, when we use a Kruskal-Wallis test, we would perform multiple comparisons using the rank sum test. This requires us to re-rank all of the data each time we perform a comparison, and we want to test at alpha star is equal to alpha E over 2M. All right, so that brings us to the end of this unit. So on Monday, we're going to start linear regression. That could be one of them. It could also be, for example, like you might be given output from an assumption check. Like maybe I'll give you a normal probability plot and I'll say, use the most appropriate procedure based off of this set of information. So then you would have to judge which approach you use based off of what you see in the plots. Does that make sense? Okay. Yeah. So in some cases, it might be median versus mean. In other cases, it would be based off of what you observe. Or based off of what you're given in terms of a preliminary data analysis. All right, so yeah, on Monday, we're gonna start linear regression. So next week is mainly review of simple linear regression. So this is all stuff that you would have seen again in Stat 151. But we're gonna go through simple linear regression in some detail, and then we're gonna start the last new unit, which is multiple linear regression. And after that, we'll probably have time for a bit of review, and then we'll be into the final exam period. So we're getting closer to the end here. Actually, it's exactly 1 month left from today. All right, so if you guys have any questions, let me know. And otherwise, I will talk to you on Monday.